Welcome to the deep dive. Today, we're jumping into something pretty fascinating in material science. We're looking at how engineers are taking epoxy resin, that super common, strong adhesive, and basically giving it superpowers with just a tiny dusting of an ultra-hard ceramic. Our goal today is to figure out the optimal recipe, the real sweet spot, for boosting standard epoxy using nano-boron carbide, B4C. Now, epoxy is great stuff. It's everywhere, planes, cars, buildings, bonds incredibly well. But it does have a weakness, a pretty significant one, actually. If you hit it hard or put it under too much stress, well, it's brittle, doesn't handle cracks very well, low fracture toughness, as they say.
Exactly, and that brittleness really limits where you can use it, especially in high-stress situations. If it might crack suddenly, that's often a deal breaker. So that brings us to B4C, boron carbide. If you haven't heard of it, it's this incredibly hard yet lightweight ceramic, think armor plating kind of hard. It also has a ridiculously high tensile modulus, around 472 gigapascals. Now, people have tried mixing fillers in epoxy before, but usually they needed quite a lot. What the researchers here wanted to do was different. They looked into the unexplored potential of low concentration formulations. We're talking really low, between just 0.1 and 0.4% by weight.
Okay, so they're hunting for the biggest bang for the buck, basically. Maximum performance improvement with the absolute minimum amount of this B4C added. Did they find it? What's the big takeaway, the aha moment?
Oh, they definitely found something significant. The main headline is that these incredibly small additions worked wonders. This research shows they got a 71% boost in tensile strength, and almost a 70% increase, 69.7% to be exact, in fracture toughness. So the epoxy became stronger, more stable, and much, much harder to crack, all without adding much filler at all.
Wow, okay, that's impressive. Let's unpack how they did it. What were the basic ingredients? They started with a pretty standard industrial epoxy, the gliidal ether of bisphenol A type, specifically Lapox L12, and cured it with a polyamide hardener, K6. The magic ingredient, of course, was the nano B4C powder. And these particles were tiny, average size, under 60 nanometers.
Right, and getting those tiny particles mixed in properly sounds critical. How did they manage that? They added the B4C to the preheated resin and then hit the mixture with 45 minutes of ultrasonication. That sounds intense, like a really powerful mixing technique. The idea being to spread the B4C evenly and stop those nanoparticles from sticking together, from agglomerating, right? Precisely. That even dispersion is absolutely key. And you can see evidence it worked right away when you look at the thermal properties. They used differential scanning calorimetry, DSC, to measure the glass transition temperature, or Chi. Chi is that point where the material goes from being hard and glassy to more soft and rubbery. And what they found was pretty striking. The pure epoxy had a TG around 52, maybe 52.5 degrees Celsius. But when they added the B4C, even at just 0.4 weight percent, the T jumped way up to over 68 degrees Celsius. That's a really significant increase in thermal stability.
And what's happening on a molecular level to cause that jump?
It tells us the B4C isn't just sitting there, it's interacting strongly with the epoxy matrix. Those nanoparticles are essentially restricting how much the long polymer chains can move around. They act like tiny anchors, holding the structure more rigidly together. This boosts the thermal performance. And they confirmed this with other analysis too, FTIR, which showed stronger chemical and physical bonds between the B4C and the epoxy. A really good filler matrix interaction.
Okay, so a stronger molecular handshake, as you put it, and that translated directly to better mechanical properties. Let's talk strength. Tensile strength. How hard can you pull it before it breaks? The numbers here are dramatic. Pure epoxy gave way at about 18 MPa. But with the B4C, the strength peaked impressively. At 0.3 weight percent B4C, it hit 31.2 MPa. That's that 71% improvement you mentioned.
Yeah, that 0.3% formulation really seems to be the sweet spot for tensile strength. The B4C nanoparticles act like tiny, incredibly strong pillars within the epoxy. And because they bond so well, that strong handshake again, they effectively take on the load you apply, shielding the weaker epoxy around them and stopping cracks from starting. It's all about efficient stress transfer.
Okay, but here's a question. If 0.3% was the peak, why did adding just a little bit more, up to 0.4%, actually cause the tensile strength to drop? It went down by about 17% from that peak.
Ah, yes. That's where the downside of nanoparticles comes into play, agglomeration. Even with that intense ultrasonication, once you get to a certain concentration, in this case 0.4%, the nanoparticles just naturally want to clump together. And these clumps, these clusters, they act like tiny defects within the material. They become stress concentration points, basically weak spots where failure starts easily when you pull on the material. But interestingly, this dip didn't happen for all properties. While the strength peaked and fell, the tensile modulus, that behaved differently. It actually kept increasing all the way up to 0.4% B4C, reaching a peak increase of 33% overall.
Okay. So why would stiffness keep going up when strength started to fail? They sound related.
They are, but stiffness is less sensitive to small flaws like those clusters. Modulus is more about the inherent rigidity of the materials involved. The B4C particles are incredibly stiff, remember. So just having more of them in the mix, even if slightly clumped, makes the whole composite harder to deform initially. They still contribute their stiffness, even if those clusters make the material break sooner under high load.
Got it. Stiffness depends on the overall presence of the hard particles, while strength is more vulnerable to the flaws created by clusters. That makes sense. So let's pivot to toughness. Addressing that original epoxy weakness, how well does this new material resist cracking? Looking at fracture toughness, KIC, measured with specific crack tests. Here, the trend was different again. It improved steadily across all concentrations. The biggest improvement was right at the top, 0.4 weight%, delivering that near 70% enhancement you mentioned earlier. 2.97 ppA M12 compared to 1.75 for the pure epoxy.
Right. And this consistent improvement, even where tensile strength dipped, tells us something important about how the B4C helps. It's about interfering with the crack's path. They looked at this with scanning electron microscopy, SEM. Imagine a crack trying to run through the material. When it hits one of these super hard B4C particles, it can't just slice through it. Instead, the crack has to go around the particle. That's called crack deflection. Or sometimes the particle can momentarily stop the crack tip. That's crack pinning. Both mechanisms force the crack to take a longer, more complicated, more tortuous path. And traveling that winding path takes a lot more energy, which is why the material becomes much tougher, much more resistant to fracture propagation.
Okay, so the particles act like tiny roadblocks for cracks. And does that improved toughness show up in impact tests too, like how it handles a sudden hit? It does. The impact strength, measured by the IZOD test, also showed a big jump. It peaked at the 0.4% concentration again, with a 62% improvement compared to the plain epoxy. Much better at taking a hit.
And then there's flexural strength, how it performs under bending. This is another interesting contrast. Unlike tensile strength, the flexural strength also kept increasing progressively all the way up to 0.4 weight%, peaking there with about a 49% improvement.
Okay, wait. So pulling strength, tensile peaks at 0.3%, then drops at 0.4% because of clusters. But bending strengths, flexural, and toughness both peak at 0.4%. Why doesn't agglomeration hurt bending strength at 0.4%?
That's a great question. The thinking is it relates to the different ways the material is stressed. When you bend something, one side is under tension, pulled apart, and the other is under compression, pushed together. The study suggests that these localized compression zones might actually help to stabilize the particle clusters. They sort of squeeze them together, preventing those clusters from acting as easy starting points for cracks, unlike in the pure tensile test where everything is just being pulled apart.
Okay. The stress state itself changes how the flaws behave. Very interesting. Now, these are all experimental results. Did they do anything to sort of double-check them computationally?
They did. They used finite element analysis, FEA. They built these computer models called representative volume elements, or RVEs, to simulate the material's behavior and predict its properties.
And the good news is, the simulations generally matched the lab results quite well. For both tensile and flexural properties, the difference between the experimental numbers and the FEA predictions was mostly within 15%. That gives us more confidence that the effects are real. Though it's worth noting the simulation assumed perfect particle dispersion, which is likely why it predicted slightly higher tensile strength at other 0.4% than what they actually measured, because it couldn't fully capture that real-world agglomeration effect.
Right, models have limits. But the agreement is still pretty good. And they also checked if these improvements were statistically real, not just random variation. Absolutely. They ran statistical tests, t-tests, comparing the modified epoxy to the pure epoxy for each property. And the results were clear. The improvements were statistically significant across the board. Even at the lowest 0.1% concentration, the increase in strength and toughness was far beyond chance. The p-values were tiny, well below the standard 0.05 threshold. It proves even a sprinkle makes a measurable difference.
So the results seem solid. Stronger, tougher, more heat-resistant, and statistically proven. Bringing it back to the real world, where could we actually see this optimized epoxy being used?
Well, given the improvements, especially the strength-to-weight aspect, the prime candidates are demanding, weight-sensitive applications. Think lightweight parts for aerospace, maybe automotive components where every gram counts. Also potentially for encapsulating sensitive electronics where you need good thermal stability and mechanical protection. And one other interesting angle the paper mentions. Because boron is good at absorbing neutrons, these composites could potentially be used for lightweight neutron shielding.
Neutron shielding. Okay, that adds another layer of potential. So wrapping this up, the core finding from this deep dive seems pretty clear. Sometimes less really is more, especially if that nilus is a tiny amount of nano-boron carbide mixed just right into standard epoxy. You get a dramatically better material, stronger, tougher, more stable, without fundamentally changing the base resin or adding a lot of weight or cost.
Exactly. It's a really elegant optimization. Now, the study did highlight one practical challenge. The mixing method, solution casting, while pretty good, did start to struggle with clustering above that 0.4% level. Reproducibility might become an issue if you push it further with that technique. And that leads to a final thought, something for you to consider. The immediate uses are clear, lightweight, strong components, maybe even shielded ones. But this study really focused on the initial properties. It didn't look into long-term performance. So the question becomes, how does this enhanced material hold up over time? What happens after years of thermal cycling, vibration, or environmental exposure like you'd see in a real aircraft part? Understanding that long-term durability, the fatigue life, that's really the next big step for this promising nanocomposite.